All right, in the last video, we were looking at this example with the rental cars where the state of the system represented the probabilities of being in either Orlando or Tampa. We considered a scenario where you start in Orlando, so the probability of being Orlando is 1, and the probability of Tampa is being 0. And then we used a transition matrix, which was the probabilities of transitioning from a given state, indicated by the column, to a given state, indicated by the row. And we use that to compute the new probabilities at future points in time. And we derived the analytical solution that after n steps, our probability is given by a times x to the n, a to the n times x0. We multiply by the matrix n times, and then multiply by the initial condition. Okay, so what I want to do in this video is I want to look at the long-term behavior of that model and try to interpret it. And we'll first do it numerically, and then we'll do some analytical work. All right, so let me fire up Octave. And so we'd written this code earlier to simulate this process where before we were thinking about the state variable as representing the number of cars in Orlando and the number in Tampa. And so we had 5,000 cars in Orlando, 2,000 in Tampa. And we saw that when we ran that, we ended up with around 4,000 in Tampa and 3,000 in Orlando. But notice this model is exactly the same thing as the Markov change. The only thing that's to change is the interpretation of the state. Now, instead of thinking about the state as number of cars, we can think about the probability that a given car is in each location. And so we could say the probability that you're in Orlando is 1 and in Tampa is 0. We could simulate the process. And what we'll see is that we get a very similar qualitative behavior. And it looks like the probabilities, although they start out at 1 and 0, are approaching some values. And in fact, looks like the Tampa probability is a little less than 0.6, and the Orlando probability is a little bit greater than 0.2. All right, so that's a numerical solution. Let's see if we can explain this result. So hypothesis is that xn approaches something like maybe 0.58, 0.42. So something a little less than 0.6, something a little, and I think we had that actually backwards. It was actually 0.42. Orlando had the smaller probability in the long run. All right, so how could we check that? Well, first thing you could do is you could imagine multiplying by a. Let's take our x0 and multiplying by a. And if I do that twice, you'll see that we get the same answers we've seen before. And you can do 3 times, and you can do 10 times. And at that point, we're getting values that are pretty close to what we estimated. So it seems like numerically, again, we're getting something, some sort of asymptotic behavior. But again, numerical solutions tell us what the answer is for a particular case. They don't always tell us why we're approaching that value, nor do they tell us if that's a very general behavior. So let's go back to our whiteboard and see if we can justify that. All right, so notice A is a matrix, it's a square matrix. And in a previous video, we mentioned this notion that you can diagonalize a matrix. You can write a matrix as P times a diagonal matrix times P inverse, where P was the matrix of eigenvectors. And then D was a diagonal matrix with eigenvalues. Okay, so what is a to the n? Well, if you multiply that thing by itself over and over again, what you'll see is that this is P D P inverse times P D P inverse a whole bunch of times. And there's a lot of P inverses that cancel out, and so we're going to be left with P times D to the n P inverse. And so ultimately, the only thing that we need to know to figure this out are the eigenvectors and then the eigenvalues raised to the nth power. Okay? So let's actually use octave to help us with this. Let's compute the eigenvectors and the eigenvalues for A. Okay? All right, so our eigenvectors, our eigenvalues, we'll write those first. We have one eigenvalue. It's a diagonal entry here. That's 0.3. And then our second eigenvalue is 1. And for our eigenvectors, we have, I'll call it V1, is the first column of this V matrix. And notice those two entries are the same, but they have opposite signs. And so we could call that negative 1, 1 if we wanted, because any scalar multiple of an eigenvector is also an eigenvector. And then the second one, I'll just leave it as is just negative 0.6, negative 0.8. Or we could also multiply that by negative 1 and just make that a positive 0.6, positive 0.8. Since, again, scalar multiples don't affect eigenvectors. Okay, so there's our eigenvalues and our eigenvectors. And so you'll notice if you were to multiply d to the n, that's going to look like 0.3 raised to the n, 0, 0, and then 1 raised to the n. And if you raise 0.3 to the n over and over again, what happens? Well, the larger the value then, the smaller that's going to get, right? And so that's going to approach 0. On the other hand, if you raise 1 to the n, well, that's a different story, right? Multiplying by 1 over and over again doesn't change. And so this is going to be just the matrix is going to approach 0, 0, 0, 1. So the eigenvalue that is 1 stays around. The eigenvalue that was smaller than 1 goes away. Now, our P matrix was just the matrix with those two eigenvectors. All right, and so when we multiply this together, we're going to get P times 0, 0, 0, 1 times P inverse. And notice, well, let's see what happens when I do that in octave. So we'll take, I guess they were calling the eigenvector matrix V times the matrix 0, 0, 0, 1 times the inverse of V. And what you get is 0.42, 0.57, 0.42, 0.57, which both columns are the same, and they happen to be exactly what we seem to be approaching in the long run. Okay? And if you multiply that by our initial state, so multiply by our initial state, which we said was 1, 0, you'll see that we're just going to pull out that first column, and so that's our long-term behavior. Now, what is the connection between that answer and the eigenvalues and eigenvectors? Well, let me go back. Okay? If you look at that original equation, when you think about long-term behavior, that corresponds to a fixed point, right? If the system approaches a particular state, that state has got to be a fixed point. So the fixed points would satisfy x star equals a times x, right? Okay, so that's what a fixed point must satisfy. But notice, if I were to put a little 1 right there, then that equation would still be true. And that looks a lot like the very definition of an eigenvalue and eigenvector. So if we call this lambda, notice 1 was one of our eigenvalues. And that means x star is one of our eigenvectors. In this case, the eigenvector that corresponds to the eigenvalue 1 was just this v2. And so we get, find that the fixed points of the system must correspond to the eigenvector with eigenvalue 1. Okay, so let me summarize that. Make this very general. for a Markov chain, the fixed point is the eigenvector that corresponds to eigenvalue 1. And that also is the steady state solution. That's what you'll approach in the long run. Okay? So, you may be wondering, hey, wait a second. You said that the solution approaches 0.42, 0.58, or something roughly, but our eigenvector was 0.6, 0.8. Well, that's absolutely correct. So I should be a little more specific here. It's more than just the eigenvector. It is the normalized eigenvector, because eigenvectors can be multiplied by any scalar. And if we want to actually get the steady state solution, this should be representing probabilities. And the total probability, the sum of the entries in the vector, should be 1. Well, right now, the vector 0.6, 0.8 does not have its entries that sum to 1. Its entries sum to 1.4. And so doesn't actually represent probabilities yet. And so we can multiply by any constant. So if I were to say take that 0.6, I'm going to multiply by 10 to make it a 6 and 8, and divide by the sum, so that now the entries sum to 1, everything would make a whole lot more sense as probabilities, right? And if you compute 6 over 14, you get around 0.42 something. And if you compute 8 over 14, you'll get 0.58 something. So again, the analysis says that when you have a Markov chain, if you want to find the steady state solution, the way to do it is to find the eigenvector that corresponds to eigenvalue 1. And the reason that's the eigenvector that matters is that the terms that have eigenvalues smaller than 1 all go away. And you can actually show that it's not possible to get eigenvalues that are greater than 1 for a Markov chain due to the properties of the transition matrix. And so only the eigenvector corresponding to 1 sticks around. And if we normalize that eigenvector, so it represents probabilities, so its entries sum to 1. Then that's going to be the steady state solution. Okay? So all of that stuff that we spent a lot of time on in the linear algebra courses comes in handy for describing the steady state behavior of a Markov chain. The numerical solution suggests an answer, but we can verify that using linear algebra to actually prove it.